In Module 5 of Chapter 20, we're going to look at correlated Ito processes. First of all, let's recall correlation of normal random variables. Namely, if we begin with W1 and W2, and they're independent unit normals, or standard normals if you prefer, we can actually create two standard normals that are correlated. From independent normal random variables, we can create correlated random variables by this simple formula. It's known as the Cholesky decomposition, and it can be generalized whereby we can start with n independent unit normals and create n unit normals that have whatever correlation structure we desire. We only need to look at the two-dimensional case, and that's what we'll do here. So these are both normal. Why is that obvious? Well, Z is just W1. That's normal by definition. Z prime is a weighted average. Rho is a number. So it's just a sum of two normal variables. So, of course, it's normal. And if we take a look at the expected value of Z, it's going to be the same as the expected value of Z prime. It's going to be 0. Has a mean of 0. If we look at the variance of Z, well, of course, that's 1 by definition. But if we look at the variance of Z prime, how would we do that? Well, W1 and W2 are independent. Variance of a sum is the sum of the variances. So we get rho squared times the variance of W, which is 1, plus 1 minus rho squared times the variance of W2, which is 1, and you can see that we get 1. So Z and Z prime certainly are standard normals. Now the only question is their correlation. If we wanted to calculate the correlation, you recall that what we want to do, the correlation is actually defined as the expected value of Z minus its mean times Z prime minus its mean divided by the standard deviations. Of course, this formula greatly simplifies for us because our two standard deviations are 1, our two means are 0. So all we have to do is time the expected value of Z times Z prime. So Z is W1, Z prime. We multiply it all out, and then we use the fact that the expected value of a sum is the sum of the expected values. And when we do the math, the expected value of W1 squared is just 1. That's the variance of W1. And this is by definition 0. Because W1 and W2 were independent. So their expectation, their product expectation is 0. So what I now want to do is to show how the correlated Ito processes from the chapter follow exactly the same structure of this simpler calculation we saw earlier. And that is that if W1 and W2 are now independent Brownian motions, we can create correlated Brownian motions using identically the same tools that we used earlier. Namely, we'll define Z1 as W1, and we'll define Z prime as a combination of W1 and W2, and notice the coefficients are the same. It again is called a Cholesky decomposition, and again, it could be generalized to n processes if we had a need. You can, as we did a moment ago, again confirm that these, in fact, are normal. What we want to show is that each of Z and Z prime, they're both normal with a mean of 0 and a variance of t. And I'll leave that as a exercise. That Z has that property is true by definition because Z is equal to a Brownian motion. But Z prime, you need to do just a little bit of work about. We know that W1 is normal 0t, and we know that W2 is normal 0t, and they're independent. So I'll let you do the calculation to show that the variance of Z prime is also t. And let's look at the correlation. Formula for the correlation of Ito processes is the same. After all, the z's are just normal random variables. And I see in this calculation that with the exception of the presence of a t, it's the same. So this is telling you that we've now created two stochastic processes. They're both Brownian motions, and at every point in time, they have a correlation of rho. Now, we can actually summarize some multiplication rules that in many of the Ito processes that we deal with, where we're going to be doing certain multiplications, you know, every Ito process has a dt term and a dz term. And the question then becomes, what happens when we multiply processes? How do we do the math? And these are, think of these as rules, whereby if we multiply a dt and a dz, we can call it 0. Same with dt squared. However, a dz squared is a dt, and if we have a correlated dz's, when we multiply them, we get a rho dt. Why is this? Well, the basic idea is that when you're dealing with stochastic processes, you only care about square root of dt and dt. Any higher power of dt in the mathematics of stochastic processes will always go to 0 so fast that whatever term is associated with them will go to 0. So this is, if you will, a bit of a cookbook approach to dealing with stochastic processes, but it's one that's justified by the more formal mathematics. And that is what you're saying when you implement these formulas is that they're not quite right, but each one of these formulas has an error that is involved a higher power of dt, for example, dt to the 3/2, and that power of dt will go to 0 fast enough that I can ignore any term associated with that. So this is just a simple way of doing the math.